Hi. All right, now that we've officially finished our studies on mitosis and meiosis, let's do a quick summary and review what we know so we don't get confused between the two things that are happening there. So if we were just to draw a picture really quick and summarize what we know about mitosis and meiosis. So we'll do mitosis here. So if I have a cell here and I have 4 chromosomes like I did before, and I'll try to keep it, I'll have 1, 2. So I have 2 chromosome 1s and 2 chromosome 2s. So we have 4 chromosomes to begin with. Mitosis is going to be an identical split, but all I'm going to do is really, create 2 cells that have 1, 2, 1, 2, 1, 2, 1, 2. Pretend those are the same. So if this is chromosome 1 and this is chromosome 2, this is chromosome 1 and this is chromosome 2, I technically have 4 chromosomes in here, right? So here I am a diploid cell. So I have 2 copies. I have 2 times 2 here, so I have 4. Remember, in us, it'd be 23 times 2, so we're 46. So I have 4 chromosomes here. When I go to split my cells in mitosis, I now create 2 new cells, and these are identical daughter cells. Because I have chromosome 1, chromosome 2, chromosome 1, chromosome 2, chromosome 1, 2, 1, 2. I still have 4 chromosomes in each cell, but they're no longer in their sister chromatid shape. They're in single chromatid shape, but they're still 4 chromosomes. So you go from diploid to diploid. I still have 2 copies of each chromosome. Compare that to meiosis. So for meiosis, I have my parental cell here. We'll start with the same stuff. So I have, they're not crossing over, I don't want it to look like that. 1, 2, 1, 2, and then they'll go through meiosis 1, and this is where things get a little different. And remember, they start exchanging genetic material. And so this would be meiosis 1. And you went from diploid, because I had 2 copies of each chromosome, and now I only have 1 copy of each chromosome. So now I am haploid. At the end of meiosis 1, you've now created 2 haploid cells, but they're still in their sister chromatid shape, but they're not identical sister chromatids anymore. So meiosis 2 gives you 1 more split. To create, I'm going to really shrink these cells down, I apologize, to create these cells. And now they're all different. There we go. Now we have 4 non-identical haploid cells. So here you go to 4 cells. Here you go to 2 cells. These are identical, those aren't. And these are diploid, these are haploid. So there's a lot of difference between meiosis and mitosis. However, the overall mechanisms from how you get from one place to another are very similar. You still get the kinetochore microtubules, you get the metaphase plate, you get stuff like that, all those similarities, yet there's stark contrast as well between the two methods. All right, that's your summary. Quick summary. There's a lot more detail, but you got that detail. So let's now talk about, let's go back to meiosis world for a little bit and discuss the comparison between female and male meiosis, what we like to call gametogenesis. When you're talking about the actual creation of sperm and egg, and not just keeping it like this, where this can be anybody, anything, when you're actually talking about the creation of sperm and egg, we call that gametogenesis. Your genesis means the beginning, so it's the beginning of the gametes. So let's talk about that. This will be Roman numeral 6, gametogenesis. And it'll be a brief review, not like a whole unit on reproduction. That's many lectures away. So Roman numeral 6, this is gametogenesis. So let's just talk about the differences between females and males. So differences when it comes to meiosis. Differences between female and, that's male and female. So the first thing we got to know about is that in males, this is what's, there's many things different, but one of the big things that are different. In males, all 4 haploid cells that get made during meiosis produce functional sperm. You get 4 functional sperm every round of meiosis. Whereas in females, excuse me, whereas in females, you get 1 functional egg. You make 4 cells, but only 1 of them works. The other 3 are called polar bodies, and they're really, really small, and they're non-functional. So let's talk about that for a second. Let's write this out. So in males, all 4 haploid cells, produced during meiosis become functional sperm cells. In contrast, in females, only 1 haploid cell becomes a functional egg. The remaining 3 are called polar bodies. And these are not used. Our bodies basically recycle them. Okay, so that's one difference. In males, the other thing that happens with this, meiosis or gametogenesis, it doesn't begin until puberty. In females, it actually begins in utero, in development while you're in your mother's womb. You start creating your eggs while you're in your mother's womb. It's fascinating. So, but for males, this whole process of creating sperm cells and even the thought of it doesn't even occur until puberty. You have everything in place, obviously, when you're born, but the process doesn't become active until puberty. So for males, gametogenesis begins in puberty. Very much related to testosterone. And in females, gametogenesis begins in utero. In utero means in the womb while you're a developing little baby. And it happens very, very fast, actually. Within 20 weeks of development, so 20 weeks post-fertilization, you have about about 7 million egg cells already made for ladies. By the time you're born, that number dwindles down to 1 to 2 million. That's still way more than you'll ever need your whole entire life. But for whatever reason, we lose about 5 million cells during development in utero. And no one really understands completely why, of course, because you can't really research on that too well, but for ethical reasons, obviously. But it's fascinating that while if you're a girl, or think of your mom if you're a boy, for me, my eggs were made in utero when I was in my mom's, while I was developing in my mom. She was actually contributing to the health and well-being of her future grandchildren. So it's kind of interesting. My daughter, she was developing her eggs while she was while she was developing inside me. So I was actually contributing to the health and well-being of my future grandchildren, her children. So it's interesting if you think about it in a generational aspect, how for females especially, what if you're growing a little girl inside you, you really have to not only think about, okay, your direct baby that you're going to be having, but also your grandchildren are going to be affected by this as well. So that's why the health during your pregnancy, taking vitamins and stress levels and all these kinds of things come into play when you're thinking of how you take care of yourself during pregnancy. It's not just about your baby that you get to hold in a little while. It may also be about your grandchildren. And there's a whole slew of science about this. And it's called epigenetics. And if you ever take a molecular biology course in college, you'll get into that. And I wish I could just sit here and teach you all that, but I don't have time for that, so it's all great. But what I do want you to know, for the males, what happens is as soon as puberty comes, those pre-sperm sites, or sperm cells are called spermatocytes. They just constantly go through meiosis, and they really don't stop until well into like old age. And even then, males continue to make sperm for a very long time. As long as there's testosterone present and it's in a pretty good supply, sperm cells will be made. Females, on the other hand, were a little bit more complicated. So I'm going to go into the female world a little bit more, because for males, it's just straight meiosis. What you see is what you get. For females, what's happening is in utero, so let's say by 20 weeks, let me back it up for a second. So in utero, you have, this 46 celled chromosome. This is your pre-oocyte. And I always love the name of this. It's actually oocyte, and that's the name of an egg. So a pre-oocyte is the cell that's going to become the eggs eventually. So in utero, you have a bunch of these pre-oocytes. And by 20 weeks, you have millions of these pre-oocytes that are now stuck, and I'm putting 46 for chromosome count. There's 46 chromosome count. These are now arrested. They get stuck in prophase 1. And so they're stuck in the tetrad stage. And we call these primary oocytes. Primary oocytes. And so when women are born, when girls are born, you're born with 1 to 2 million primary oocytes. So these are just hanging out inside the ovary, inside of each woman, and you get a couple million in there, and they stay this way until puberty. So the hardest part of meiosis gets done in utero, making all the tetrads, the crossing over, all of that, and they just stay there in that way. And they're pretty protected as well, which is wonderful. So then once puberty hits, then we finish meiosis 1, and enter meiosis 2. But here is where the female cycle starts to begin. Once puberty hits, that's when your body realizes once a month we're going to take one of these primary oocytes and release them from the ovary in a process called ovulation. During that process, meiosis 1 gets completed, and you create this little tiny polar body that has 23 chromosomes inside, and then you create this other cell that has 23 chromosomes inside, and this is called your secondary oocyte. This is secondary oocyte. And this whole process happens during ovulation. That is when, out of the millions of egg cells, the primary oocytes you have in your ovary, one gets released. Only one. We don't do this with everybody. We reserve as much energy as possible. Only one each month gets chosen to become a secondary oocyte. And that secondary, and you complete meiosis 1, gets completed. And this secondary oocyte gets stuck in metaphase 2. So it's arrested in metaphase 2. All right. So you're wondering, okay, so every ovulation you release one egg, and it's technically not even a mature egg yet. It's only completed meiosis 1, and it's hanging out in metaphase 2. The only time women complete meiosis 2 is upon fertilization. So I have 2 children. I've completed meiosis twice. That's how it works. So once a month you release this oocyte. If it doesn't get fertilized, it goes through your system, and now if you've reached puberty, that's the menses that happens every month. If it does get fertilized, then you get to grow a little baby. But if the cell gets fertilized by a sperm, then and only then does that second meiosis happen. And here's the little polar body. See how small these polar bodies are compared to the egg? The egg is basically stealing all the cytoplasm, everything it can from all these other cells, because this is the one that's going to have to grow a baby. And so it's like, give me everything you have, because I need to grow a baby, and we don't need to have, just take everything from this one. And then this one becomes the fertilized egg, and it becomes 46 after that. So because 23 from mom, 23 from dad makes the 46. And then this one also realizes it's got to split as well. So it's interesting, the polar bodies know what to do. So the only time you complete meiosis is upon fertilization. It's pretty fascinating. So in the female anatomy, it realizes don't waste energy if you don't need to, because there's a whole lot of work that has to happen if that fertilization event does happen. So, but if it doesn't happen, every month you release an egg. If no fertilization happens, you release it, do it all again next month. But you have 1 million to 2 million hanging out, waiting, and you will not use them all in your whole entire lifetime. That's more than we need. So they just hang out in there. But that is one of the big differences between females and males. And this is why the female anatomy is a little bit more complicated, if you will, during the puberty years than the male anatomy, because there's all these arrestings going on and stuff like that, whereas males just go straight through. And that's just, it works, because obviously we're all here, so it works. So that is officially the end of section 5 for cell division. And what I love about it is that you not only realize that if I damage a cell in my somatic cells, mitosis will help repair it, because it'll bring back all the cells that got lost. And ultimately, when it comes to reproduction, here's how gametogenesis works and how it is meiosis. And so how genetic variability occurs through crossing over, independent assortment. Those are huge events that happen during meiosis to give all the beautiful variability that you have in front of you. So I hope you all enjoyed it. And I hope the worksheets are helpful to help you just kind of review all your work, and the test goes well. So I will see you next time. We're going to start genetics and bring all the stuff that we learned with a little bit of genetic variability from meiosis and actually apply it in our genetics studies. All right, thank you. And I'll see you for section 7 or 6. Yeah, 6. Bye.